Hello, everybody. Thanks for joining our fourth session of this Victor short course. So today we're going to focus on Tephra fallout models, and I'm going to quickly introduce the Tephra 2 model through the advection diffusion equations. And then after that, I'm going to show you all to run the Tephra 2 on Victor and to be able to do the little homework exercise that we prepared for you. That's going to run Tephra 2 to actually find out what is the loading, the Tephra loading on some different type of buildings and whether these buildings are prone to collapse or not. So I'm going to share my screen. Right. Everybody see my screen? I'm good. Okay. So I want to start by introducing the Tephra 2 model first. So Tephra 2 is one of these models that is called an advection diffusion model, which is different from other type of Tephra fallout models that are called particle tracking model. That's going to track volcanic clouds in the atmosphere. Tephra 2 is not doing that. It's only looking at accumulation of Tephra on the ground as a mass per unit area. So it's been written by Laura and Chuck Connor and Costanza Bonadonna. It's been updated through several versions. So we have a forward model that we're gonna go through today, and that you guys are gonna use. And then we also have a probabilistic model that is looking at surviving function and exceeding probability of Tephra at a particular location around the volcano. And then there is also an education model that is a little bit more simple to use. But all these versions of Tephra 2 are using the same algorithm. You get some input parameters here that are the eruption parameters, particle parameters, some atmospheric parameters, and then some grid parameters. And then we actually integrate the advection and diffusion equation, and we solve them as different height above the vent of the volcano, and with different grain sizes for the particles. And then in the end, we look at the mass per unit area, so the distribution of Tephra around the vent as a mass per unit area. And you also get a weight percent of each of the grain size fraction around the vent. Right, so the goal of the model is really to calculate the accumulation of Tephra around the volcano in the case of an eruption. And so the end product is actually isomass map that is showing you the mass per unit area that you can then convert into an isopack map, which show you the thickness of Tephra around the vent. So how the model works. So we've got a series of vertical steps around the vent. So we're going to discretize our eruption or eruptive plume into different layers. These are horizontal layers above the vent. And then for each step up in the eruption column, we're going to have a range of particle sizes from a minimum grain size to a maximum grain size with some weight percent. The distribution is a Gaussian distribution. That's one limitation. You cannot actually have something different than a Gaussian distribution, which fit most of the grain size distribution for Tephra fallout. Then we're going to calculate the probability of particle size release at each column time step and calculate the particle fall time from a point release source. And that's going to be modified by atmospheric diffusion. Well, first by column diffusion, so inside the column, and also by atmospheric diffusion. That's going to produce a spreading of the particles. It's going to fall through the layered atmosphere. different horizontal layer of the atmosphere, and it's been advected by the wind. And these particles are going to eventually fall into the ground and accumulate as a mass at each grid location, X and Y. So the unit is going to be the kilogram per square meter.
It's muted. Yeah.
Question for you. What do you do in the winter? Riding a bicycle. You don't ride around?
You're unmuted.
Okay.
If you would like it, I don't know if you could fit it in your place.
Can we unmute?
Okay. Just for like to put on my own note.
Okay, I'm just muted. Sorry, let me go back. All right, so these are the advection diffusion equation here. So we got the first term here, which is the rate of change of the mass concentration of particles in space as a function of time, dt. Then we have these two terms here are for the advection of the wind. So Wx and Wy are the downwind and crosswind component of the wind velocity. And then we have to subtract the terminal settling velocity of the particle for different sizes. So Tephra 2 assumes that the particle has spherical particles with different terminal velocity based on their sizes. And then on the other side of the equation, we have the diffusion terms here. K is a horizontal diffusion coefficient for Tephra in the atmosphere. And we can see that that's a second partial derivative of the concentration as a function of a distance, x, to the square. Then we do the same in the y direction. And then finally, we add a source term here, which is a change in particle concentration at the source with time. So you can see already that we have a few simplification here, which is that layer atmosphere, horizontal layer of the atmosphere. So the wind is going to be constant inside each of the layer of the atmosphere. So it can change between layers, right, above the vent. But inside each of these layers, the speed and the direction of the wind are going to be constant. And we can see also that we have a constant diffusion coefficient, K, here. There is only an horizontal diffusion coefficient, so we don't change the diffusion of the particle vertically. So we assume that the terminal velocity is actually much greater than the diffusion, so we don't have to do that. So these are the few assumptions of the model. So yeah, we have this advection, right? So just for those who are not sure about what is advection, you're actually pushing your cluster of particles in one direction, x or y, in these two different terms here. And then you have your diffusion that actually are related to the spreading of the particles across a density gradient inside the same space, right? And then you're going to do this in X and Y as well. So it's two-dimension model. Then you have your terminal settling velocity here that change at different elevation. That is mostly based on the Reynolds number. And then here you have your source term, which is the mass ejected during the eruption. So you're looking at the change in mass concentration at the location through the eruption. So this is the result parameter, basically, that you get. And this is just a summary of the different terms in this advection diffusion equation. So a little sketch to show you how that works. So we have volcanic vent where the eruption is going to originate. We're going to drop particles at different height above the vent through this layered, horizontally layered atmosphere. These particles are going to be spreading through diffusion inside the column itself, and then it's going to be also spreading through diffusion in the atmosphere, and they're going to be advected by the wind, and they're going to fall on the ground, and we're going to measure that accumulation of tephra at specific ground location. So the eruption parameters that you need to input into the code are the plume height, which is the maximum eruption column height, as of meters above sea level, not above the vent. Then you have the eruption mass in kilograms. Then you have the diffusion coefficient in square meter per second. And so, yeah, Tephra 2 is very sensitive to these three parameters that are the most important. Then there's other parameters like the eddy constant, which describe atmospheric diffusion. So usually for the Earth, we use this Fickian diffusion parameter, which is 0.04. Then we have a diffusion coefficient. Like we were saying, this is a constant, and it's only a horizontal diffusion coefficient, tend to range between 100 to 10,000 square meter per second. We have a 4x threshold that describes the transition between a linear diffusion and a diffusion governed by a power law. So when you look at a graph of square root of isopac against distance, and then you have different segments there that actually describe the change of the setting velocity and the diffusion. You can actually do that by defining that breaking slope in the graph by using that 4x threshold. And then you can also input different densities for the lyrics and the premise. If you have different components in your Tephra, and you know the componentry and the density of this class, then you can put it in there. So in summary, we have a series of steps from the vent to the eruption column top. For each particle size, we determine how much drops out and how much stay in the plume. And then for each of those particles that pass through a layer atmosphere, they are pushed by the wind and they're spreading through diffusion. So these are some references about the model itself. Paper from Suzuki, 1983, mostly focusing on the diffusion. And then paper from Chuck Connor about estimating volcanic hazard from Tephra fallout. And then paper from Costanza Bonadonna about probabilistic modeling of Tephra dispersion. There is also a usual user manual. Sorry, I'm gonna get to it. So that you can download. I guess we have a link on the Victor website. This is a user manual here. In case we don't have a link, I'm gonna share it with you now on the chat. Right here. All right, we have a question. Why does leading and pumice density are related to the size of the particles and not on the actual dense and porous tephra that can be erupted? Not sure what you mean here, Roberto. These are only the density of your particles, right? So it's basically the same for different sizes. So it's only you're using only a mean density here for the entire distribution. Yeah. So there's no variation with the size. Yeah, that could be something that can be one improvement of the model. All right. So if you go into the education folder for the course, you're going to see a week 4 folder in our shared folder, and there's this different files in that week 4 folder. You can copy the entire folder into your directory, and we're going to go through 2 notebooks very quickly that are going to explain in a bit more detail how we can use the advection diffusion equation to solve them and then play with some parameters. And then there will be also the take-home as a PDF file, the take-home exercise that we're going to go through quickly that you guys are going to have to run during the week. So I'm going to start with the advection diffusion notebook here. So as you can see, we have the same equation as I was just describing um, in the PowerPoint. So we having it here summarized as well at the beginning of the notebook. And so when we try to implement these equations, what good thing to do is to actually look at the dimensionality of each of the term, right? So for example, we can take the first term here, which is the rate of change of the concentration of the particle in space as a function of time, and I can replace that term with a mass divided by a length to the cube times a time t, right? Um, so I can do that for each of the term here, and I can replace, each of these terms by the dimension related to each of the components of this equation, and I ended up having something like that here, as you can see. And that's pretty useful because then you can try to check, which terms are the most complex that you may want to simplify, or you can also find a way to actually convert some of these dimension into some numerical terms. So that's what we're going to do here. We're going to say, okay, let's forget about the setting velocity term, this one here. Okay, we're going to get rid of it. So we're going to rewrite the equation and drop the setting velocity term. So that's what we are getting here as equation number 3. So you can prove to yourself that the units still work out fine by using the same dimensionality exercise we did before. And then what we're going to do, we're going to try to implement these equations using a finite difference method. So this is one of the methods that you can use. You remember that Mattia last week showed us different ways of solving equations, partial differential equation. One of them was the Eulerian solver. And so Tephra 2 is actually using the Eulerian solver. But here, we're going to just use the finite difference because it's a little bit easier to use and to explain. So I'm going to switch to the other notebook to show you how we can rewrite the diffusion equation first in a finite difference scheme. And then we're going to briefly see how we can do that also for the advection. And then finally, how we get the full equation. So we have here a diffusion equation in 2 dimensions. Here we just replace k by alpha, but otherwise we can see that this equation here, number 1, is actually the same as this equation that the right hand terms here of the diffusion terms here in x and y. We're going to see the same here. That should be y here. Sorry, there's a typo. And so when we apply a finite difference method, we're actually going to look at each of these term t here, and what we're going to do, we're going to separate them in 2 different time steps. So we're going to use k for here the time, and we're going to say, okay, this change here of here we use temperature for t. This change of temperature or as a function of time can be rewritten as the temperature as time k, and then the temperature at time k plus 1. And if we want to get the difference, right, of the temperature at 2 different time steps, then we're going to rewrite this as the temperature at k plus 1 minus the temperature at k as a function of time, right? And then we're going to do that for each of the other terms that are here. And we're going to, again, discretize that based on here, the I function, the I parameter, and J parameter. And so in the end, we're going to actually get an equation here that is similar as this one, but that at least that we can try to solve numerically, okay? And so to do that, we're going to assume that the space in X and Y are the same, okay? So we have a regular grid where X and Y are the same dimension, the same distance. So we're going to rewrite that equation by using S for delta X and delta Y. So we ended up having that equation here. And then we can solve for the maximum time step that depends on the grid spacing and the diffusivity. So what we do is that we put this delta T parameter on the left-hand side and then everything else on the right-hand side. And then we can rewrite this to simplify it using this term here. And then finally, if delta X and delta Y equal S, we can just end up having the square of S over 4 times alpha, the diffusion coefficient. So by doing this simplification, I can actually implement that now as a code. So I can import my libraries needed. Just need NumPy and the matplotlib to plot my results, and I can start to actually implement my diffusion equation in 2 dimensions. And to do that, I'm going to actually here simplify it. I'm going to actually use the function that is already made from a textbook from Geria that is called Numerical Geodynamic Modeling, which is actually this one, Introduction to Numerical Geodynamic Modeling. I'm going to put that in the chat for you guys. So you can check that book. It's a really cool book to actually get a lot of to learn a lot about numerical modeling in geoscience and geodynamic, and it comes with some predefined function, which are okay, a little bit like a black box, right? But then the good thing is that you can directly define them on a Jupyter notebook, and you can call that function here that is called one-time step together with the parameters, input parameters that it needs. And you can directly actually run that in this notebook. So you can see here that the input parameters we need will be the velocity at the source at time step t equals 0. Then we need the velocity at the next time step u, so k plus 1, for example, here. We need a diffusion coefficient. We need a time step dt, and then we need some source dimension in x and y. So we can try to implement that diffusion in 2 dimensions. So we're going to say, okay, the width and the height of the source are going to be equal to 100 pixels or grid space. The interval in x and y dimension are going to be equal to 1. The thermal diffusivity, we're going to take the example here of an intrusion, of a granitic intrusion into the crust. So we're going to say that the diffusivity in the granite is 10 to the minus 6 square meter per second. Then we're going to implement the temperature. So we're going to say, okay, we're going to go from 200 degrees to 1200 degrees C. So 200 will be our lower temperature, and then 1200 will be our highest temperature. And then here we got some other terms about some terms for the source, and then we got our time step here. I'm going to go back to that time step later because that's one of the major input parameters that you need to calibrate. And then here we have our source, so initial flux or velocity here, and then our velocity at times t plus 1. And so what we're going to do, we're going to integrate, we're going to iterate that over 100 time steps and see what we get. and then finally we're gonna plot that. And here we go. We're gonna actually calculate the time that it takes to actually diffuse that heat from that intrusion into the wall rock. So you can see here that we have the heat that is diffusing, and it takes about 300 days to actually get that diffusion over the grid here that we set up. So you can play with that notebook by changing the number of time steps, and you can also try to change this DT value by putting another relationship here, and then see how much that affects the diffusion. It was just one example to show you how we can actually implement that diffusion in 2 dimensions. So we're gonna keep that function here as a diffusion, and we're gonna go back to the advection diffusion notebook where we're gonna implement this diffusion here for finite difference approach, and then we're gonna add the advection. So same as for the diffusion, it also comes as a already made function that you can call. It's using what we call the Lax-Wendroff method for the advection. That actually is one of the way to implement the advection equation, but there's many other that can be used. So if you want to know more about the implementation of advection in 2 dimension, I would refer you to Matthias' book about principles of numerical modeling in geosciences. And he's got different chapters here, 6 and 7, for example, that are related to numerical solution for the diffusion equation here, chapter 6. Chapter 7 is actually for linear advection. So you can go through them. They are all chapters are in a Jupyter notebook, so it's pretty easy to actually go through this. And you will see that he's also using the finite difference scheme. Same as us, forward time, center space, and then he's actually changing that. He's going a little bit further down to actually implement a little bit more improved scheme. I'm not going to go into detail here, but just to let you know that if you want to know more, you can actually go through these notebooks. But here, the scheme we're going to use is that Lax-Wendroff, and so we just implemented here in that notebook. So we're going to do a test run. We're going to take our advection diffusion functions, and we're going to set up a source that is placed near the center of the grid. And that source is going to emit some heat, and that heat is going to spread in the grid, and it's going to be advected as well. So here's the test we're going to do. We're going to define our width and height of the grid to be 5,000 grid space. The interval is going to be equal to 10. And then we're going to put a wind speed here, which is -5 meters per second, which means that the wind is going to blow toward the west, right? So from the right side to the left side of the grid at 5 meters per second. We're going to keep the temperature as the same as what we did for the heat diffusion of the intrusion. And then we're going to set up our diffusion coefficient here as 100, because this time we want some particles or heat or gas heat to be spread out. Oops, and then I got an error here. Please don't define. So probably I forgot to import we will run it by importing the libraries first. Okay, so it's giving me here my time step, which is 0.2. So again, this time step here, as you can see here, is defined only as dx divided by 10 times the absolute value of the wind speed in the in the x direction. So like we say here this timestamp needs to be improved. And for that, I refer to Matthias' notebooks to see how we can improve that time step. Remember, by either looking at the error, absolute error or relative error of your solution, or looking at the adaptive time step that's going to change with time. All right, so we're going to iterate this over 1500 time steps. It's going to take a little bit of time, and then we're going to plot the results. They're going to be basically the advection and diffusion of particle, for example, out from a vent. So I have to wait a few minutes here. And we can calculate the time that it takes for this particle to be advected and diffuse. Okay, 300 seconds. You can see here that our source is at the center of the grid, and then our particle is first advected to the northwest, and then it's diffusing and spreading on the other direction. So we're going to try to improve that by saying, okay, we're going to take the same script, but now we're going to change the location of the source, and we're going to allow the wind field to vary spatially, right? So we're going to modify that Lax-Wendrock advection function, and we're going to introduce a new term here that is the change of the wind, the change of the wind field in one of the two directions. So we're doing that using here that line that allow for the change of the wind, and we're going to implement that again, same as we did before. We're going to run that over 9,000 time step, and this time we're going to plot that, and you're going to see that this time it's actually looking more like a band plume that is spreading particles towards the west. And so you can actually play with the notebook to actually change how high that bend in the plume is occurring, for example, or how high above the vent the particles can actually go. So it's just a little notebook just to show you how we can actually implement this advection and diffusion equation in 2 dimensions. So of course here, remember that the particles are not falling into the ground, they're just spreading and being advected into the atmosphere. And so this is a simplified case that allow you to see how we can implement these equations. So you can try to play with the diffusion coefficient to see how that affects the spreading of the particles. You can also try to play with the time step, trying to find another way to define the time step or to increase it or decrease it. You can also play with the grid spacing. Here you will see that if you increase the grid spacing and if you increase the time step, you're going to start getting some instability. Numerical instabilities that need to be corrected. So, all right, that takes a little bit of time, more time than I thought it would be, but eventually the results are going to be there. So feel free to play with these notebooks and try different things and look at them. There's also here more applications that you can do. So for example, how would you modify the code to make the plume bend over at a given height, right? So for that, you can consider the Briggs equation, where the maximum plume center line is defined as this function here, where F is a buoyancy parameter, and U is the horizontal wind velocity, and S is the atmospheric stability factor. So you can try to implement that Briggs equation to modify the code and make the plume to bend over a specific height. And the second thing you can do is also here consider gas advection and diffusion in dry volcanic system. And then using these two equations here, you can try to implement these expressions in the advection diffusion model. So permeability, for example, so buoyancy-driven flow velocity is based on some permeability and gas pressure, and then using here a density. Oops, yeah, here we go. So that's the results. I don't know if you guys managed to get it as well, but that's basically what you get, and that's showing you that Z value over which the plume is bending above zero, zero being the ground elevation. All right, so that was for the first part. Let's now move to. Is there any questions? Let me stop sharing my screen for a second and go back to the chat. All right, I don't see any questions so far. So let's move to what we wanted to do, which is running Tephra 2, right? So let me share my screen again. All right, so first thing you guys are gonna do is go into your Victor workspace here, and you're gonna open a terminal. Okay, so the terminal is located here for me, but if you just open a new window in your workspace, and you're gonna see that link for the terminal, and then in the terminal here, you're gonna type Victor setup. You press enter. Oops, setup without a space. And then you get a list of models here that you can install on your home directory, and you can see that Tephra 2 is at number 19. And so, by the way, we have other codes related to Tephra Fallout, High Speed, for example, and ASMAP here are other example that you can also run on Victor. And I guess we're also gonna have a 3D pretty soon. Sam, I think it's on the way to be implemented. So I'm going to type the number of the model here, 19, and I'm going to type enter. And here, of course, I got a message saying that Tephra 2 folder already exists, but for you, it's going to install a new folder in your directory here called Tephra 2. So if you open that folder, you see there's two files, one called Tephra 2 2020, which is an executable, and then one that is a Jupyter notebook. So that's the one you want to open here. And that's basically the notebooks that you will use to run Tephra 2. So I'm going to skip through the text here because it's basically summarizing what I explained at the beginning of the class. So you can see here that there's a couple of libraries you need to make sure you install first. So make sure you install these libraries, and then first thing you need to do is to enter the coordinates of your volcano, right? So you can see these coordinates is actually coming as a latitude and longitude number in degrees, decimal. So make sure you put a little bit more than 1 decimal here after the dot, because otherwise the location is not as precise as what you may want. So make sure when you select your location that you put as many decimals as you can here to get a precise location that should be the vent of your volcano. Then you have the eruption parameter file. So we're going to read that. So we're going to import that DEM here, which is, I think, DEM around South Sister volcano in the Cascade in Oregon. And then here you can see that we got these parameters that I was talking about at the beginning that are very important for Tephra 2, which are the plume height, the eruption mass, and then the median grain size and the standard grain size. So make sure that you put these parameters in there, and then you got additional parameters here. So Sam, I got a question for you. The 0 here doesn't mean that the parameter is actually equal to 0. It means that it's using the default value, correct?
Yeah, exactly.
Okay, cool. All right. Because I was not sure. So yeah, for example, like for the parameter density, or it doesn't mean that we use a value of 0. It means that it's using the default value from the code, right?
Yes, yes. Yeah, I think if you scroll down a little, it should show basically at one point it says it basically checks if value equal to 0, replace with a default.
Okay. All right, great. Just wanted to show you, explain these two parameters here because these have changed over the year. At the beginning, Tephra 2 was actually using a constant column width and height. So then these have changed to like some ways to actually define a shape for the eruptive column. And these two parameters are actually related to that. So you got the explanation here. And it's using a beta distribution. So the beta distribution, if you just like go on Wikipedia and look for it, it's actually looking at, it's like a power law that is having two parameters for the shape of your power law. And you can see here, for example, that based on the value of alpha and beta, I can actually change the shape of that power law. So if you assume that that x direction here is your elevation above the vent, so if you rotate that by 90 degrees, right, toward the right, and then you have that as a y-axis, you can actually define where you're going to release your particles above the vent in the plume. So, for example, if I follow that orange distribution here, I can see that in that case, so which is alpha equal 2, beta equal 5, I'm going to release most of my particles in the upper half of my column, of my eruptive column, right? So that's how basically you can define where you want to release particles inside the column. If you don't want to release particles at a particular location above the vent inside the column, and you want it to be all homogeneous, then you just leave the values by default. All right, then you have the grid file, which is basically your input parameter for the grid in terms of spacing, grid radius, elevation. And then here you have a cell that allows you to put some specific location around the volcano where you want some data out of it. And that's going to be useful for doing the homework exercise because you're going to have to choose some specific location to try to record the isomass at that particular location. So you can do that here on that cell number 9. Then we're going to specify a wind file. So for that, we're using the reanalysis data. And then you can specify the year, the month, the day, and the hour of your wind file. So we're going to import the wind data here and then create netcdf file that's going to be used by Tephra 2. And then we're going to make the configuration file that Tephra 2 needs to run. So that's the next cells here. So it's very important that you wait that these are done before going to the next step. So you can see here now that we have all the files needed here that are created on my directory. So you need really to wait for these files to be created before running. Otherwise, you're gonna running Tephra 2. Otherwise, you're gonna get an error. All right, and then you can run Tephra 2. It's gonna take a few seconds to run that. You can see that there's some new files appearing on the left. Especially this Tephra 2.csv. This is your output. So you can then now go into the other cells that's gonna allow you to actually plot an isomass map of the simulation. And the cool thing with using this output, this plot from Victor, from the Victor notebook, is that it's actually showing you also the location of your three location or two, like depends how many locations you want to run the vent together with their isomass value. So here we go. So you can see that you got your isomass map here in kilogram per square meter. So each line is labeled. We go from 1,000, 155, and 1 kilogram per square meter. And then you can see here your three locations that you put in cell number 9 that are here together with the exact value of the isomass that are corresponding to this location. So that's pretty important because you will see, now I'm going to switch to the homework that you guys will have to do. And you will see that you will have to actually take these values and put them into a table there. All right, so this homework is actually asking you to run Tephra to simulate the dispersion of volcanic ash from an eruption and to assess how the eruption conditions are going to impact the infrastructure that are surrounding the volcano. And for that, we're going to use a hypothetical eruption at South Sister volcano in the Cascade. Some links here to Tephra 2 and Victor. You can actually download the Tephra 2 manual. Here we go. There's a link here. You can also watch a tutorial. So it's going to allow you to know a little bit more about how to run Tephra 2. But with everything that I just said, I guess you guys have a good idea on how to do that. So the first part of this homework is actually to pick up some location points, right? So remember, I was showing you in cell number 9 that you can pick up locations. So that's what you're going to do here. You're going to pick up 3 locations that are around South Sister volcano, 1 in Bend, 1 in Redmond, and 1 in Sun River. And you're going to record the latitude, longitude coordinates of this location. You're going to measure the roof area using Google Map, and then you're going to define what is the type of roof for each of the buildings that you're targeting here. So this is a description here, step by step, how to do that. For that, you can use Google Maps actually to do that. So for example, I can show you if I use Google Map quickly here how to do that. If you right-click, I'm in Tampa here, but if you right-click on a location, you can get the exact coordinates here. And then you can also click on measure distance. And then you're going to click on so for example, if I zoom in, I'm here. So I'm going to take that building here. I'm going to click on here. And I'm going to say distance to here. And I'm going to click here, distance to here. here, distance to here, and then distance to here. And if you do that exactly, which I didn't here, you can actually get the area. Yeah, you need to match exactly the, how was it? Okay, maybe if I zoom out. Yeah, here we go. You can get the area written here at the bottom. So you're gonna need this area for the roof in order to calculate the loading. So you can do this for each of your building using Google Maps. That's for the first part. So once you've done that, then you can actually run Tephra 2. So you already done that. Installing, make sure you install the Tephra 2 code. Then you're opening the Tephra 2 notebook. Then you're gonna put the location of the volcano, southeaster, with these coordinates here. And then you're gonna enter the coordinates for the 3 sites that you selected in the part 1. So make sure you enter the locations that you got from Google Map. And then you're gonna run Tephra 2. And then the second part is gonna ask you to fill that table here, right? So for each site, you're gonna run Tephra 2 3 times with different eruption volume. 1 cubic kilometer, 3 cubic kilometer, and 5 cubic kilometer. And then for each of that, you're gonna give me the erupted mass, what is the deposit mass area at the site. You're gonna convert that into a deposit load, and then finally a total mass on the roof, okay? And you're gonna do that so for these 3 different eruptive volume at each site. Okay, so there's some tips here how to convert from volume to mass, and then from mass area to mass per unit area to load. And then finally, you can answer the following questions here: which direction did most of the output travel from each location? Calculate, and then these steps here are the one that I was just describing to actually fill up the table. And then finally, you can look at page 7. That is a detail of the type of roof, together with how much load you can have before the roof collapse. So your job is going to be to, based on which building you selected from each of your sites, try to define a roof class for each of these buildings, right? Based on this description here. And then from that, you can actually define a threshold over which ash can actually accumulate on that roof before the roof starts collapsing. So you can do that, and then based on that, you can actually answer these questions here for site 1 and eruptive volume 1. Did the roof collapse, yes or no? And you can do that and fill up that grid with your correct answer. And that's basically it. So try to do that during the week that is coming. We can leave you more time to do that for sure. And if you have any questions, let us know. So let me see in the chat. If we previously installed Tephra 2, should we put the Victor setup? No, you're good. Yeah. If you already have installed it, don't reinstall it anymore. The files haven't changed. So it's okay to use all these digits for the coordinates. Well, I mean, you don't have to use them all. Try to use at least, I would say, 3 or 4 after the decimal to make sure that you're precise enough, especially because it's only one building, right? So it's a pretty tiny point over the whole grid area. So you want to make sure that you put enough digital enough decimals to actually get that location precisely. So yeah, if there's any question, please use the Slack channel or the chat. here to ask your questions, comments, or anything, and we'll be happy to help you. And I believe there's also office hours coming in, Sam and Sophia. So if you want to stay and then try to work on this exercise during the next hour, you can ask any questions you want to Sam and Sophia during the office hours. And if there's any questions, we have 3 minutes left. So I don't know if Sam or Sophia, you guys want to add something. Oh yeah, how do they send their homework? Are they using the Padlet again to do that? What's the best way?
I think so. Yeah, for now, the Padlet. I've been trying to work with 2I2C to get some kind of group folder set up, but that's been a slow. So Padlet for now.
Okay. I'll send an email anyway with the link to the Padlet again when I send the recording for this session.
I guess the one small thing I'll add is that we did recently add a kind of variation of the Tephra 2 notebook, if you're curious, that does some predictive it does some predictive calculations based on I forget exactly what it is, but it's like these future wind patterns. So if you want to just poke around with that, that's another kind of fun addition that we have to the platform that was within the last month or two.
Okay. Roberto asked, new Padlets or the same from Take Home 1. I think we're gonna create a new folder for you guys to upload your results. I think Sophia can do that. And
Yeah,
then,
it'll be the same link, but we'll make a new tab for this lesson. And yeah, I think someone has a suggestion about the best way to upload onto Padlet, but yeah,
yeah, I mean,
can send some information.
I checked them the other day, and HTML file is great. If you want to put the whole notebook, it's working as well. I was able to open the notebook. So if you want to put a notebook with your results, if you want to edit the PDF as well, you can do that. But I think maybe the best would be a Jupyter notebook with your results. How do you estimate the grain size parameters with the field data? I mean, how can I say that the X side is a representative medium grain size or the total grain size distribution of the eruption? Yeah, that's a good question. So, of course, one limitation of the Tephra 2 is that it's assuming a Gaussian distribution, which we know that even if it's the most common distribution we found on Tephra Fallout, we can have other distribution, especially a bimodal, especially when you have ash aggregation, for example, clusters of particles, forming moisture in the plume. All these can actually, or turbulences, right, of the wind during the advection and diffusion of your particles. So all this is not taken into account by Tephra 2, and it's only assuming a Gaussian distribution from a minimum and maximum grain size. So that's something that I think some other models are going a little bit further, like Fall 3D. If I'm not wrong, you can actually input some more complex grain size distribution and going away from just the Gaussian. And yes, you're right. The best way will be to actually calculate the total grain size distribution of your eruption based on many outcrops around the vent, right? And then use that total grain size distribution as an input to the code. So that's something you cannot do in Tephra 2, but again, I think other models like Fall 3D are actually allowing you to do that. All right, I think time's up. If you have any other questions, don't hesitate to use the Slack channel and stay for the office hours just right after that. if you guys want. Otherwise, yeah, see you next week. We're just starting a series of surface processes. So today was Tephra fallout. Next week is going to be lava flows, and after is going to be PDCs, and then after is going to be lavas. So stay with us if you want to learn about modeling of each of these surface processes. Thank you guys, and see you next week. Have a good weekend.